Thank you everybody for joining. We're going to talk about building a data lake on AWS. I'm Johnathon Meichtry, a Principal Solutions Architect for Amazon Web Services. I'm really excited to be talking about building a data lake on AWS because it's coming up quite a lot with customers. Our objective today will be to give you an idea of what we see as a data lake challenge and give you some design patterns for building a system aimed at supporting people who consume data in your organization. Once upon a time, the enterprise data warehouse was the center of the universe. It gives us a lot of benefits that we've taken advantage of for many years. Those benefits include things like a self-documenting schema for our data, very concrete and enforced data types so that people couldn't make mistakes and interpret data in the wrong way, a common security model, and of course you get easy access to your data warehouse using standard SQL tools. The data warehouse also gives us some interesting capabilities around the transactionality of our data so that we can entrust it with the financial systems records of our transaction processing systems. These are all really important business attributes that we have to consider when we think about defining and building a data lake and setting priorities for what a data lake even needs to be. One of the things an enterprise data warehouse does is that it very tightly couples compute and storage. The idea is that you push your business logic into the data warehouse and build stored procedures and views which sit right alongside your data. From there, you can scale that environment to meet your business objectives by adding cores and RAM and have highly available storage, which is also highly durable. So our enterprise data warehouses have gone a very long way to solving very complex business problems. But we are seeing customers with new and evolving requirements. The data in your business could need to be more agile, it could need to be more accessible, or maybe you need to be able to work with data which doesn't necessarily fit into a pre-specified schema. Maybe you now want to leverage pure in-memory tools for natural language processing. Maybe you have a particular requirement to solve a graph problem and struggle to do it with SQL tools. And so let's consider how we've moved forward and address some of these challenges over the last few years. To address those challenges, we have seen the rise of the Hadoop ecosystem. And on AWS, Elastic MapReduce provides us with a runtime for that ecosystem which leverages the storage environment on S3. It lets us build highly robust, scalable, and diverse engines that can solve lots of different problems. One of the things that the Hadoop ecosystem and the big data ecosystem allowed us to do was to take that tightly coupled compute and storage and break it apart. This way, we could run lots of compute on a system that was independent of the job we're trying to accomplish. So big data technologies have gone a long way of implementing this concept of a data lake. But is our Hadoop environment sufficient to be the data lake? When we think about the benefits of separating out compute and storage, we're able to get a lot more low cost and cost efficiency because we're focusing on providing the necessary compute solely to fulfill the storage requirements. We can do really interesting things like independent cost attribution for different pieces of data within the storage environment. Rather than looking at an enterprise data warehouse and saying, well, there's an overall cost, we can look at what it costs to store an actual business unit's data. This sort of architecture gives us the ability to choose the right tool to solve a problem at the right time. Running Elastic MapReduce clusters with Spark, Presto, Hadoop Streaming, HBase are kind of good examples. Whatever you require is available on demand, and you choose that tool because it's the right way of expressing a solution to the problem. We also have this really nice ability to increase the durability of our data. And we use that term a lot. What does it mean? It means how safe is our data? And so how do we provide extremely high durability to our data without doing a lot of operations and managing that on a Hadoop cluster? And we can also move towards this idea that a data lake really tries to achieve, which is a common model for data storage without enforcing any type of access method. So the big data technologies are really just a start towards building a data lake. We need to talk about what are the other things which give us the same kind of benefits that an enterprise data warehouse has delivered for many years and go much further than what we can get from just a big data solution. So let's quickly look at some of the differences between an enterprise data warehouse and a data lake. If we compare big data versus an enterprise data warehouse, you know they are very complementary. And you can expect that your big data environment may be producing data for your big data warehouse. And separating compute and storage gives us some really great benefits, like providing a model on read semantic First is a model on write that we have to use when we ingest data into a relational database. Big data solutions give us much better agility. We should be able to ingest data very quickly because we don't have to go through an analysis process to pull that data in and make it available to end users. If we look at what an enterprise data warehouse was good for, it was really, really good at reporting. It was also really good at business intelligence, but as soon as we want to do things like predictions, plus those reporting use cases, we start to hit some very challenging problems. Also, we typically have to make a concession on the amount of data that we're able to push into our enterprise data warehouse. Although with services like Amazon Redshift, there is such a disruptive price point, we're able to really start ingesting everything into a data warehouse, but how far do you go? For example, would you go to the extreme path and put all of your network traffic from your platform into Redshift? You might do that, but there can be other ways of solving problems with gigabit per second datasets by using decoupled architectures. So we have two systems which are really kind of at odds, and they both are serving great requirements within our business, but often created another problem. The problem is that the two don't overlap very well. So do we duplicate our data between an unstructured system and a structured system? Is our enterprise data warehouse populated from our big data environment? And how do we enable these other tools to work against data sets which are in the enterprise data warehouse? And ultimately, we need to synthesize these two domains together. What we need is the ability to harmonize these two sources, and this is an objective we will set for our design of a data lake. So what does the system do? Well, the big data component, the unstructured data management systems, are doing things like ingesting any type of data at scale and in a very agile way, such as doing things like massively parallel data cleansing. And we can also move towards this idea of having a data catalog which sits outside of our enterprise data warehouse environment. For example, when a database DBA does a described table, they get the table comments. That's an extremely useful feature, but how do we extend that same experience to all of our data? And that process that we employ should then be used to push data into a more structured environment for things like analysis. A very common pattern is to pre-aggregate at the store everything forever level. And we still benefit from implementing structured business rules within our enterprise data warehouse. There is also a huge amount of value which we have captured in the enterprise data warehouse that we may need to use to solve other business problems. So in other words, exporting computed aggregates, business rules, etc., so that we can do things like trend analysis and implement machine learning. It's quite a nice pattern, and you can see how they can work together very well. So a data lake really needs to support this idea that an enterprise data warehouse is just another projection of our company's core data. But it isn't the only thing we use to solve a problem, so that the benefits we've been getting from an enterprise data warehouse have to live in other places as well. So the components which we are going to walk through include the base storage capability for data, but also our ability to work with streams. A data lake can't just be a massive pile of data at rest. It also needs to be able to support the idea that things are changing all the time. And our storage and streaming layer needs to give us extremely high durability. A design pattern that we recommend to our customers is that the storage tier should store raw data as you first captured it. The moment that you reduce the granularity of the data that you store, you are losing business information. Okay, some data you don't need to store, but as soon as you decide it would have been better if you hadn't deleted it, then you're most likely out of luck. The storage API needs to be able to store any type of data and allow us to respond when a business user comes to us with a new piece of data to store. When they do, we can respond with, yes, absolutely, we can store that in the data lake. And to have that full take architecture, it needs to minimize cost. And not just low cost, but low variable cost. We're able to put data in the right sort of system that gives us the cost profile that the data justifies. On the streaming side, streaming isn't just about pushing data in. Streaming also allows us to look at ways to move away from a file-based ingest architecture to a stream-based one. Also the ability to turn around and say, what if I wanted to consume a piece of data from my data lake as a stream? What would that look like? Because it's quite neat. If every time a piece of data changes and I was able to consume just that change, there could be some really interesting business solutions and enable new ideas to be fulfilled. The first component of a data lake that we would ask you to consider is that a data lake is more than just storage. It is not just a pile of data, but it has this ability to document itself. That is, enable data discovery, and that can facilitate our end users being more productive with the data. So we need a data catalog, the home of all the data lake's metadata. And what this is going to do is that it's going to give us summary statistics about our data. It'll also do things like classification. A really simple problem we need to solve with our big data systems is, show me all my data for a particular customer. How do we do that? It's actually really hard. And then on the other side, search is increasingly important to our customers, who need to be able to just discover patterns in the data, see where data is related, and expand on that picture. For example, situations where we thought data wasn't stored about a customer, but in fact, we can discover there is data where we didn't think there was. Search can enable us to find that. It's a really important component of our data lake strategy. The next thing we need to consider is what we call entitlements. Entitlements include security as well as things like authorization, regionalization, chargeback, quotas, and masking. All of the things that you may need to implement to be compliant with your business practices. Customers that use S3 can store any type of data, but in many cases, they're going to end up with ubiquitous access or no access at all. And so we need to consider the problem fully, and we're going to give you some patterns that you can consider implementing depending on what your requirements are. Lastly, we need an API and a user interface that exposes this environment to the outside world. Our data lake design is comprised of AWS services, and they all have APIs. But gaining access to this environment isn't necessarily as simple as just exposing those AWS APIs to your customers, because you likely have very complex business rules that you've implemented in your entitlement system, and those absolutely have to be respected. Our data lake API is a way that we implement governance of the system, because human policy-based controls can be extremely hard to get right. So first up, storage and streams. What does it look like? The Amazon S3 Simple Storage Service provides a foundation for any data lake we build. But there are things to consider about S3. S3 has a very flat key space. And if you ingest 100 terabytes of data into S3 and then decide that you don't really like how it's organized, you've got a very big job on your hands to change it. So we recommend that you spend time up front on how you design your data on S3 to give yourself the most flexibility possible. You see, doing things like naturally taking advantage of the partitioning that your data gives you and using a prefix structure that lends itself to a more intuitive interaction with data will be beneficial. So what does that mean? Well, you might decide that you have a common way of storing data on S3 that possibly takes the business unit, the application name, the type of data that you're storing, and maybe even time as a key component of how you'd organize that data on S3. And once you've made that decision, stick with it. And make decisions about how you change it very, very carefully, because we're going to use this almost as a basis for a metadata catalog. S3 is a service designed for you to store a virtually unlimited amount of data and do so with a durability design of 11 nines. And when you talk about keeping data safe and the durability measure, you can think about 11 nines of durability as if you had stored 10,000 objects in S3, you could theoretically lose one of those in 10 million years. That's what 11 nines of durability means. And even with 11 nines of durability, we go to great lengths to CSE check and provide checksums of your data and allow us to store data on the magnitude that S3 is built for. When we talk about what data can be ingested into a data lake, S3 is completely open to storing any type of data you want, from a tiny 1 byte object all the way up to 5 terabyte objects, and it's happy to store absolutely anything. See, S3 isn't a file system, it's object storage, which means you can access it over HTTP. We can put it in any type of data, and it only looks like a file because it has a file name and a MIME type attribute. The AWS SDKs and client tools allow you to work with file data as though S3 was a very simple file system. S3 is also a regional service, so that when you create a data storage environment and you choose a region that's appropriate for you, S3 is implemented across all the availability zones in that region. By design, we won't move that data outside the region, and with services like AWS CloudTrail, you can ensure that data is journaled and audited for how it's being used. S3 supports concepts such as access logging and identity and access management capabilities to make this data extremely secure. And then we can take advantage of things like server-side encryption, as well as client-side encryption to make sure it's even more secure and ensure we can only use it for permitted tasks. So S3 is a really great system for ingesting anything and then helping us manage cost. S3 also has lifecycle integration with Amazon Glacier. Amazon Glacier is a service designed for cold storage, also offering us 11 nines of durability, but with a retrieval time for our objects of between 3 and 5 hours. And now you can also take advantage of a feature of S3 called S3 Infrequent Access, or S3IA. S3IA is a much cheaper option that is still giving us online access to our data, but at a significantly reduced cost. And S3IA is a perfect feature for use for data that you almost never need access to, but whenever you do need to get to it, it's immediately available. And one of the great benefits that we can take advantage of in our storage system is that S3 will manage this tiering for us. S3 lifecycle integration allows you to write a policy that says, after a certain period of time, move my data to S3IA, and then after a further period of time, move my data to Glacier. And yet after another period of time, delete it entirely. Lifecycle policies do the work for us. So with all these features used together, we can look at our data coming into our data lake and determine the right cost profile for our data. So what is this data and how do we store it? Well, consider when you use S3 as a foundation for your data lake that not all file formats are created equally. You're going to have totally unstructured data. You're also going to have some semi-structured data that is likely going to change over time, and you're absolutely going to have very structured data. But across all of those different types of data, we really do want to store the real from creation copy of the data. Having access to the original raw data allows us to recover and almost replay the business if ever needed. You could implement a downstream workflow to do things like standardization of your data, implement data cleansing, and so on. But it's absolutely vital that you consider some structure which allows you to store everything as you received it in the first place. At the same time, you want to store a picture of what happened as time progresses. And as you store that data, you should use a data format that is sympathetic to your data rather than forcing everything into a data format that you decided to enforce historically because we used to normalize data to one format. But you'll want to do things like having a common approach to compression. You want to pick your compression capabilities so they allow you to work with data and do things like transparent decompression streaming and so on. And a crucial part of how you store data and the data format you use is to consider how it will change over time. When you choose to store all your data in formats such as awk or Parquet, you have to consider what happens when it changes in the future. And is the format going to be able to deal with that change? So for unstructured data, it's actually really simple. Store the native file format, i.e. logs, dumps, dump files, etc. We really do mean store everything. But we want you to use a codec that allows you to stream data and work with it on systems like Hadoop very easily. We recommend LZO compression because it gives us good compression. It's only about 20% bigger than zip, but it's a streaming codec. And it has client tools on Linux and it's supported by most Hadoop tools. Semi-structured data such as JSON, XML, whatever the case may be, this is an area where we really need to think about evolvability. A data format like Avro can be very useful for allowing you to assimilate schema changes of the data over time. And an interesting ability is to store with an SC an attribute on a given file that says, well, where is the schema for this piece of data? Where can I look that up if I needed to? On the structured side, lots and lots of data is CSV. Legacy systems such as mainframes, application servers that were built many years ago are probably going to be able to generate CSV. It's a very common interchange format. But this is also an area where you may ask yourself, do you use Parquet or awk? Because they have lots of similar attributes as CSV, but they provide massive compression. But be very careful when selecting one of these data formats because you may find that you need to work with a tool in the future that doesn't support these data formats. In other words, do everything to keep your options open. On the streaming side, it's a real complement to our storage architecture. Data ingress and egress of our data, so we need to be agile and consume not only at the granularity of files, but consume lots of other data types too. Streams matter because there is more and more customer focus on latency between an event occurring and being able to take an action on that event. A typical enterprise data warehouse and even some big data systems would target maybe hourly latency as an objective. But with streaming, it's going to be in the 1 to 2 second range. And building an architecture around streams can help us facilitate these use cases, but it can also be more complicated to operate. And so when we consider how we integrate streams into our data lake, we need to consider the business value that we receive from having a streaming approach. So Kinesis gives us this great ability to handle streams both inbound and outbound. And with tools like Kinesis Firehose, we can have a fully managed delivery of data inbound to S3 automatically. Kinesis gives us that streaming capability to build real-time analytics systems, and the storage is extremely durable. In a similar way to S3, the shards within Kinesis are implemented across multiple availability zones. They give us very high durability, and we can have as many consumers of that data as we require. So the archive and ingestion use cases that Kinesis Firehost enables can be complicated with things like sliding window analysis using Sparks, and automatic load into our enterprise data warehouse in the form of Redshift, and building sophisticated event processing systems. So if we look at a Kinesis architecture, it interacts with our object store in a slightly subtle way. Our analytics applications, of course, are going to be reading and writing file data, but we also have the ability to move away from files. At source, we can take a file and just stream it onto Kinesis. That gives us a great benefit. On our application tier, we can throw the file away. We don't run out of disk anymore because we've made every single event durable on the stream. Those analytics applications are going to be reading and writing from the streams, but we also implement the idea that we want to replay history of our data lake by having a component which takes a specification for a piece of data on S3 and fetches the object and injects it back into Kinesis so that applications can reconsume that piece of data. And when using streaming for inbound data storage, we push that into S3 for long-term storage and archiving. So now let's cover catalog and search. The catalog is really about giving us an aggregate picture of the data we have stored in S3. It gives us the ability to define new metadata characteristics, define things like ownership of data. Not in terms of ownership of an object on S3, but a much more abstract sense of ownership. It gives us the ability to think of things like lineage. For example, I inject a piece of data into the data lake and later on it's moved somewhere. We need a component that will track that history. And so the data catalog is this abstraction layer. For example, if we wanted to identify data owned by a customer, we aren't limited to just simple prefixes on S3. We could also easily span multiple S3 regions using our catalog, thereby moving the data closer to where it's owned or needed. And this will help us use a resource-oriented approach to expose this data back to our customers, and it gives us a nice API for our entitlement system. If you're not familiar with resource-oriented architectures, we recommend reading about them on Wikipedia. It's an interesting idea that comes out of the way in which we would structure a web API, that we would expose resources and then operations we can perform actions against. Resource-oriented architectures help enable some really interesting ideas for how we might lay out data on S3. For example, organized by system, application, year, type of data. Or we might have tagging and resource markers within our data that facilitates building really interesting integration patterns where we could use S3, the S3 prefix, as a key for working with very complex data on our primary integration system. So, one of the components of our data catalog is a metadata index. It needs to store information about S3, so this is going to be things like the total size of the objects in S3, the number of objects per prefix, a data classification. For example, imagine sensitive data and you have to have a certain entitlement to touch it. When was it last refreshed? Or is it versioned? These type of questions. And with this pattern, we would recommend you consider using Amazon Lambda to process events to build this metadata index. With Lambda, you can do it very easily and store the metadata itself in DynamoDB. So look, we chose to implement our metadata index in DynamoDB because it has some really great characteristics. It can be a document store. It can be a key value store. It gives us multi-availability zone durability, and it can be scaled on demand. And AWS Lambda is an environment that implements simple logic without having to run any servers. And in fact, building a metadata index is a fairly trivial problem to solve using AWS Lambda. For example, let's say we receive a new object into S3. We need to make a record of the object arriving. So we store its metadata as a summary, we increment counters for the size and object count, and we add prefixes. And the powerful thing is that Lambda is able to scale automatically with the volume of data that's coming into a data lake. On the search side, we want to be able to take all these different systems which are pushing their data into S3 and give us some standardization with how we interact with that data. And search systems are going to tokenize the contents of our files. It's going to deal with cases in different languages and so on, and also index and match data together. And so we can use services like Cloud Search and our new Elasticsearch service that are extremely simple to use, with high durability, high performance, and don't require any operations to scale. So we build on our metadata index by capitalizing on DynamoDB update streams. Update streams give us the ability to consume the change being made to DynamoDB using a streaming interface coupled with Lambda events. So every time we add a new component to our data lake, it gets registered with our metadata index, and that metadata index emits an event, and then we're able to go and read that file and index into our search system. With this, we end up with a very sophisticated metadata catalog where an object created and object deleted is being run through our Dynamodb metadata index. Lambda sits at the heart of transparently maintaining the search index for us. A very simple pattern that allows you to build whatever attributes you require into the Dynamodb metadata index and take advantage of Cloud Search and Elasticsearch for your search interface. So, entitlements. Entitlements give us the ability to not just treat this data store as a massive miscellaneous collection of data objects, but instead allow us to finally secure our system. One thing that we think is important is that a data lake does not completely mean open access to all data. There may be some kinds of data where you're comfortable storing in a public context for your business or customers or internal users, and that's okay. But in the same way that an enterprise data warehouse gives us a common security model, we need to consider that a data lake or data going into a data lake is going to include your most important and sensitive data. So we can't just leave it open for anyone to access. Identity and access management is a system within Amazon Web Services that allows you to secure data on S3 and manage users and groups and roles in a very sophisticated fashion. It's based on a policy language, and we're going to look at some of the ways you can use that against your S3 environment to secure your object storage. The policy language is not just a static point-in-time definition. It also has this concept of dynamic variable resolution. This definition includes things like user ID, username, how users have authenticated, and so on. So you might use IAM for controlling access to some of your openly accessible data. By this we mean possibly open to anyone inside your business. And in this case, the only restriction you may have is using a secured transport. Other data could be secured in different ways. For example, what if I just want to let people write into my data lake, but to only read data, they've got to be authenticated as the owner of that data. So you can write a policy which includes the list and the put and uses their AWS username. And then that's all they have permission to access. That's a really nice example of a statically defined yet dynamic policy for securing data in your data lake. AWS IAM Federation also allows us to extend that definition of someone all the way to an Active Directory environment. And so directory services allow us to run an AD connector, and then all of this policy language and all of the security you're going to be able to build using IAM is based on existing user roles in your business. But we do see cases where we need to extend further and build more user-defined security, taking advantage of things like our data classification policy. And this is where the idea of a token vending machine comes in, otherwise known as TVM. The TVM allows you to implement business rules for your temporary access to your data lake. The token vending machine allows IAM security token service plus other business rules to decide if you have the ability to access something. And the TVM is going to be combined with encryption, whether that's Cloud HSM, the AWS Key Management Service, or just simple server-side encryption to do things like control access to our encryption keys. For example, we've encrypted our data, but we also need to control whether or not people even have the right to decrypt the data. So let's look at how entitlements would work end-to-end. First, we build a customer master key, and that generates customer data keys. And then we encrypt our data. Next, we push that data into S3, and we can only do that because we have a temporary token which lets us do encryption. Now, you might have a policy which says anyone can generate encryption keys, and that's okay. But there could be very sensitive encryption keys which you need to control access to on the basis of some control mechanism. So there's a ton of flexibility in this approach. An example of how you would use an entitlement system with a token vending machine to build a very secure data flow is shown on this slide here. Your users don't just push data into S3 or consume data from S3, but instead they talk to an API which talks to your token vending machine. It checks your metadata index to determine if the customer is operating in a context in which they should be able to access the data. They then get an STN token back, and they encrypt the data using encryption keys. Then they're allowed to push that data into S3 because the STS token gave them access to do it. It's a really nice pattern, but we can reverse it for a GET request. It would work exactly the same way as the put, but it's a GET instead of a put. Lastly, we need an API and a user interface which exposes this. While S3 is the foundation for our data lake, customers can no longer just go and browse all the data in S3. They have to work through our data lake entitlement system. So you may find that when you build your data lake, that IAM is adequate for your security model, but as you move further and further towards building things like data classification into metadata index, this concept will become increasingly important. The API is going to be extremely important to expose our token vending machine mentioned earlier. You can do things like exposing services through any language you already use. You can implement any runtime, whether it's Docker, Beanstalk, or maybe even Lambda functions. API Gateway has some really nice features. It does caching, throttling, it does some really useful things that our data lake API will require, and we really encourage you to consider using it as a part of your data lake design. So whether you're going to syndicate your data internally, externally, all your API calls are going to go via CloudFront and then hit the API Gateway. This gives us caching, monitoring, and implements our endpoints using AWS EC2, whatever the case may be. So ultimately, our API and UI architecture sees our users fundamentally get access to the API gateway through IAM or through something like an Active Directory policy. We may implement our user interface within Elastic Beanstalk and drive that with API Gateway. But ultimately, the token vending machine and the Lambda are really working against our metadata index most of the time to give us a token which allows us to access our data. So this is how it all looks. A data lake needs to be a foundation of extremely durable storage. The ability to consume that data and archive it through a streaming interface, and crucially include a metadata index and workflow which helps us categorize and govern data that is stored in the data lake. We add to that metadata index with a search index and workflows which enable us to discover new data. We also need to focus on a robust set of security controls. So if we can implement controls within our data catalog which dictate when people can create copies of data and how those copies are secured, we end up with the data governance rules being built into the system. Then the API gives us the ability to enforce our entitlement system. This isn't something to leave up to chance. You can't afford the possibility of data leakage from a system like a data lake because its core purpose is to store everything important to your business. In this diagram, we can see at a very high level we have a foundation of S3, Kinesis, and Glacier for our storage and streaming. We have a data catalog implemented on Dynamodb and a cloud search or Elasticsearch index providing search capabilities, all supported by AWS Lambda as our data orchestrator for this flow of data through the data lake. And then our entitlement system has at its heart a token vending machine which provides temporary access credentials fundamentally based upon the information in our metadata index. This gives the flexibility to define any type of rule we require. Sitting at the top, the API and UI expose the data lake to your internal users on your internet, or potentially you can even securely expose this as a service to your customers. The concept and definition of a data lake is still evolving. The ability to absolutely store everything in an original or sympathetic format is very compelling and will make it possible for you to invent new ways in the future to view and consume data from your business systems. To gain more confidence and hands-on experience with AWS, watch our instructional videos and explore the self-paced labs. Attend our instructor-led classes by qualified AWS instructors and learn how to design, deploy, and operate highly available, cost-effective, and secure applications on AWS. Validate your technical expertise with AWS and use practice exams to help you prepare for AWS certification. Get more information at aws.amazon.com/training. Once again, I'm Johnathon Meichtry from Amazon Web Services. Thank you for attending this session about building a data lake on AWS. Do provide us with your feedback and let us know how we can improve the event experience for you in the future.